And hello everyone. So here we're going for part 3. So with all of that functional analysis out of the way, we can actually get started with our applications. And the first of these is we're going to be dealing with the F-series in both a more generalized and a more systematic way. And for this, we first need to begin by expanding slightly our notion of what an F-series can be. Just as a heads up, the expansion can go even further, but for the current purposes, we'll stick to this because otherwise things are going to get pretty complicated very quickly. So let P be a prime number, and for each j from 0 to p minus 1, pick a non-zero rational number, rj. Then, these should be r's, we define the formal series s, r0 rp1. Well, this is going to be the following series. It is the product of rj to the number of j's in the p-adic digits of z mod p to the n. So just as a caveat here, the j equals 0 case is special. We define the number of zeros in the p-adic expansion. We define it as the total number of digits, lambda p of the integer, minus the sum of minus all of the other digit counts. So the numbers, so that they automatically are rigged to satisfy the identity that the sum of all of these exponents over j is equal to the number of digits, p-adic digits in the input. And so what this F series does is it's a sum of products, and in each product, the number of the exponent of rj corresponds to the digits. So now let's just describe the convergence properties here. So let L be a prime of Z, including the infinite prime. If Z is a non-negative integer, our F series will converge in QL if and only if R0 is less than 1 in L adic absolute value. Likewise, let L be any finite prime of Z. Then if Z is in ZP prime, meaning it has infinitely many non-zero p-adic digits, then our F series converges in QL if and only if the L-adic absolute value of the nth term goes to 0. And additionally, if Z has infinitely many non-zero digits, then this will a sufficient but not necessarily necessary condition for this to converge in the reals is if the lim sup of the of 1 over n times the weighted sum here is going to be less than 0. The proof here is that if z is in n0, then z has finitely many p-adic digits, and so in particular, this is going to end up becoming a geometric series in R0, which will then converge L-adically if and only if R0's L-adic absolute value is less than 1. On the other hand, if z is a zp prime, this is then, if L is a finite prime, then this is exactly what it means for this series to converge in the non-Archimedean L-adic topology. Finally, we get the real convergence criterion by applying the root test, which says that since this is the nth term, if this is less than 1, it converges, and then to get this condition, we just take logarithms. So, using our frame theoretic formalism, given a frame F, thick or thin, on ZP, which is compatible with a given F series, S, we can make sense of S as an element of this locally convex ring of rising continuous functions. Did I explain how rising? Yes, a rising continuous function, or even as an element of the metrizable topological ring C rise bounded. Note that if S is compatible with F, then S is automatically going to be an element of C of F. And then, of course, we can also get this as C bounded if it's bounded in the specific norm. And so the topological, in particular, the topological closedness of C, or the bounded rising functions in C rising is really nice, because then it lets us take view the active summation of this series. If we instead replace this infinite upper limit with a finite number, then this is going to be a locally constant function, and it will be an element of both C rise and C rise bounded. And then in particular, taking the limit of the sum just means going from passing from this space to this space. And so this is really nice because it's going to allow us to seamlessly pass back and forth between F-series and the functional equations that we can associate with them. So this is a really important construction, and this will end up significantly generalizing not only the work that we did in episode 3, but the work that I did in my dissertation. So, but remember, back in episode 3, we spent a great deal of time showing how we constructed chi-q from the constant term of composition sequences of the branches of TQ, and then we established the functional equations, and then we showed that we got a rising continuous function from the 2 adics to the q adics. Now we're going to do all of that, all of the episode 3 stuff, but for the polygenic case and at light speed. So rather than work with the hydra maps directly, let's instead start with the system of functional equations. So let P be an odd prime and fix non-negative rational constants, alpha j and beta j. Technically, we can make these, here the beta j's are free to be negative, but I just want to keep it simple for here. And here we're going to require that alpha 0 is between 0 and 1, beta 0 is 0, and that alpha j is non-zero for all of the j's. And then we're going to consider the following system of functional equations. F of Pn plus j equals alpha j f of n plus beta j, and this is going to hold for all non-negative integers n and for all j from 0 to p minus 1. Note that a more hydra map-like formulation can be recovered by writing alpha 0 as a over d and then setting bj to equal beta j d, and then we end up getting this formula. Anyhow, setting n equals j equals 0, we get that f of 0 is equal to alpha 0 f of 0 plus beta of 0, which is alpha 0. Since alpha is not equal to 0 or 1, when we simplify this to 1 minus alpha times f of 0, we can cancel, and this forces f of 0 to be 0. By induction, just as we did in in episode 3, we can then use this to get a uniquely determined solution, chi, of these functional equations defined on the non-negative integers. And the way you do it is recursively. First, we know what f of 0 is 0, so then we figure out f of 1 by evaluating this when n is 0 and j is 1. Then we figure out f of 2 when n is 0 and j is 2. And for every j in this set, we figure out values of f of 0 to f of j by considering j and with n equals 0. Then we consider this with n equals 1 and j varying, then n equals 2, j varying, etc. And that will build up our function completely recursively. Yeah, and so again, there's the example. Now we're going to introduce the key hypothesis. Suppose that for each j from 1 to p minus 1, there is a prime number qj, so that the qj adic absolute value of alpha j is less than 1. In other words, what we're saying is there is some, for each j, there is some prime so that the map x gets sent to alpha j x plus beta j is a contracting map in the qj adic topology. Yeah. And so by induction, we can then get that a recursive application of our system of functional equations tells us that if chi is the solution for the equation, then formally the limit as n approaches infinity of chi of z mod p to the n is going to be this. It's chi of j0 plus j1p plus j2p squared, where all of the j's are from 0 to p minus 1. This is then beta j0 plus alpha j0 times all of this, which is then beta j0 times alpha plus alpha j0 times beta j1 plus alpha j1 times all of this, blah, 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 and we get beta j0 plus alpha j0 beta j1 plus alpha j0 alpha j1 beta j2 plus blah, blah, blah. And so we just note here that the nth term of this sum is beta jn times k, the product from k equals 0 to n minus 1 of alpha jk, whereas per our convention, this product is defined to be 1 whenever n is 0. We can express this as a function of z by noting that when z is in zp prime, the jk's are the p-adic digits of z via z's Hensel series representation. And so we just then count. Because the jk's are taking values from 0 to p minus 1, we can simplify this product by saying it's going to be alpha to the number of k's for which jk is 0, alpha plus the number of k's for which jk is 1, etc., which is, of course, just counting the digits of z mod p to the n. And so we get that this is precisely equal to this when we make the identification that z is the p-adic integer whose p-adic digit sequence are the chosen jk's. And so, voila, we have this, that the limit as n approaches infinity of chi of z mod p to the n is the limit as n approaches infinity of n equals 0 to n minus 1 beta jn times this product. So now let's just determine the convergence behavior. Well, first of all, note that modulo the constant term, this is just one of our F series. So if z is in n0, then the only digit that occurs infinitely often in z's expansion is 0. And so in this case, we'll be able to express this thing as the sum of finitely many terms by simply we pick n to be big enough so that z mod p to the n is actually equal to z, and then this thing will stop growing. Yeah, and then indeed that limit is going to converge in the discrete topology. Now it's also worth noting that this freedom of choice, and in particular because this converges in the discrete topology on the non-negative integers, when we pick a frame to make chi a compatible function, we have a freedom to choose our frame to have any topology on the non-negative integers. And this freedom of choice is actually built into the series formula. Indeed, if we evaluate this series formula like so, we can pull, for a given non-negative integer z, we can pull out all of the terms for which n is greater than or equal to lambda p of z, the number of p-adic digits of z. And then in this case, we have that here, where is it? So let's see. When n is bigger than or equal to lambda p of z, jn is going to be 0, in which case this is beta 0, and we defined beta 0 that was specified to be 0. Likewise, this just becomes the number of j's in z's p-adic digits. So this term over here vanishes, and we're left with this finite product. And so this is a formulaic verification of the fact that this sequence converges in the discrete topology when z is a non-negative integer. So now let's deal with all the other j's. Then examining our formula, since the qj's are prime numbers, then in this case, the q-adic absolute value of the decay of this to 0 is precisely what we need in order for this series to converge q-adically. Because remember, when you're working in a non-Archimedean space, infinite series converge if and only if their terms tend to 0 in absolute value. And so we end up with that. So, and indeed, the p-adic digit counting principle is our observation that z in zp will be in zp prime whenever that z will be in zp whenever there is a single j such that both of the following occur. J occurs infinitely many times in z's sequence of p-adic digits, and alpha j has a q-adic absolute value less than 1. So the idea that we're doing here is, recall we picked our alpha j's so that each alpha j was divisible by a prime number qj, so that alpha j's qj absolute value would be less than 1. So in other words, as long as z has infinitely many j's in it, then this product will converge to 0 qj-adically as n goes to infinity. And so what we then have is that the rule is, in order to converge qj-adically, we need for z to have infinitely many j's. So in the biggest case, we have that our p distinct primes, actually it's p minus 1 distinct primes, q1 through qp minus 1. If for any given z and z prime, this limit converges in at least one of those topologies, but potentially in more than one. So for example, if p is 5 and z has infinitely many 1s and infinitely many 3s, then this limit here is going to converge Q1 adically and Q3 adically. So this gives us a great deal of freedom to choose a frame, because it's like the situation we saw last time where we had that 3-adic and 5-adic convergence, but now there's even more combinatorial properties. So the way we're going to do this, just as a recipe for constructing a particular frame, is we're going to, it's going to be a Q frame, and we're going to produce it by constructing sets which partition ZP, and then we'll determine what the frame should be whenever based on what set Z happens to be in. Here, I'm using the first approach I gave to frames, where I'm defining the frame as it's a map which accepts an input from the set and produces a valued field. So here, letting Q0 equal infinity, so that Q infinity is the reals. Let's define U0 to be N0, and then we define f of Z to be Q to be the reals, Q infinity, whenever Z is in N0. Now, for every J starting from 0 to P minus 1, we're going to let Uj plus 1 be the set of all Z's which are in ZP, but not Uj, such that they have infinitely many J plus 1s in their p-adic digits. So U1 is going to be the set of all p-adic integers with infinitely many 1s digits. U2 is the set of all p-adic integers with infinitely many 2's digits, but only finitely many 1's digits. U3 is the set of all p-adic integers with infinitely many 3's digits, but only finitely many 1's or 2's digits, etc. And then we have our frame is going to output the QJ-adic topology if Z is in UJ. And thus, and the way it works is, if Z is in UJ, Z will have infinitely many J digits, and thus will be convergent in the QJ-adic topology. And using this, we then have that chi is a compatible function, and our recipe is that the limit of this is interpreted QJ-adically depending on which UJ Z happens to be in. The thick frame approach that I used could also be used here. In fact, that would then give the biggest possible frame that we could use. In there, the frame, what we would do is we would output the semi-norm, which for each Z, it measures, the semi-norm has all of the topologies in which this limit can converge at that given Z. And then with all of those semi-norms, we would then have our space of compatible functions with its locally convex topology. And so indeed, one of the elegant things about the semi-norm approach is when you formulate it in those terms, you no longer need to worry about the distinct choice of frames. Instead, you just consider all of the possible semi-norms with which you get pointwise convergence, and then that tells you everything you need to know about the F-series. Now, what's really important here is the fact that not only have we, once we have constructed a frame for making sense of this limit, this condition plus the functional equations will then uniquely characterize chi and the associated frame. And so, in particular, what we have is the following theorem, but first I want to give you some terminology. So let P be a prime number, let K be a global field, and let F be a K-frame on X, where X is some set in ZP, which contains the non-negative integers. Given chi from N0 to K, I say chi is F rising continuable to ZP if there's a rising continuous function, chi prime, so that the limit of chi of Z mod P to the N converges to chi prime with respect to F for all Z in X. I then call chi prime an F rising continuation of chi and say that F raises chi from N0 to X. Yeah. So, and then this is important. If the F rising continuation of chi exists, it is unique. This is because it depends only on F and the values that chi takes on N0. So consequently, I'm going to abuse notation the obvious way, and I will write chi to denote both the function on N0 and its rising continuation. With that, everything that we were arguing above shows the following. let P be an odd prime and fix non-negative rational constants alpha j, beta j, where for j from 0 to p minus 1, where alpha is between 0 and 1, where beta 0 of 0, and alpha j is non-zero for all j. And then for each j from 1 to p minus 1, we're going to suppose there is a prime number qj, so that alpha j has a qj adic absolute value that's strictly less than 1. I'm going to call this hypothesis here the contraction hypothesis. Then there's a unique function from the integers to the non-negative integers to the rationals, satisfying this system of functional equations. And for each frame which raises chi to zp, there is a unique function such that this equality occurs, where the f of z is on top of the equality to tell us that both sides of this equation are occurring in this field. And this uniqueness occurs when we require chi f to satisfy the limit, that it's the limit of chi of z mod p to the n with respect to f. Note that we can, I wrote this up before this goes to show you how busy I've been. I wrote this up before I realized I could use semi-norms to reframe everything. So if we were to use the semi-norm approach, then what we would just do is find the biggest frame with respect to which this limit converges, and then then the setup works, and it's just everything. So we don't need to worry about the different choices of frames. And so the important thing is because chi of z mod p to the n is taking values in Q, everything makes sense point-wise, because the limit that we look at depends on what z we pick. So the corollary of all this is that let all the constants and chi be as given, the previous theorem, up to and including 1. Then there is a bijective correspondence between frames which raise chi to zp and rising continuations of chi to zp. And we can subsume all of those different frames into a single frame by using the thick frame formalism. Now we have the connection between our F series and chi. So SR0, Rp minus 1 is a formal solution of this system of functional equations. R0 Rp minus 1 of Pz plus k is equal to Rk times the F series of z plus 1. Moreover, for any p-adic integer z and any prime L, including the infinite prime, the following hold. This function, the F series at z, converges Q in QL if and only if Pz plus k converges in QL for at least one k in z mod Pz, and if S of Pz plus k converges in QL for at least one k in z mod Pz, then this converges in QL for all k in z mod Pz. And the proof is it's just entirely formal. We just argue directly. So Pz plus k, that goes here. Then we pull out the n equals 0 term, and this here is going to be 0, so this becomes 1. And here we use the way that this works, the fact that when you apply, because of the functional equations satisfied by the digit counting functions, we can then apply those functional equations and reduce the congruence here by 1. And then this, of course, gets us. This acts like the indicator function, so this will be 1 when j is congruent to k, and so the only term here that survives is when j is equal to k, and we accrue a factor of rk. Then we reindex by increasing n by 1, and we're get that. And this proves 1. The key property to know is that all of these manipulations are valid, provided the z that we've picked makes it so that this is convergent. So that's, again, everything is happening point-wise. Once we know that the expression converges at a given z, all of these manipulations are perfectly legal. Now, for 1 and 2, right here, fix a z and zp, and suppose L is a prime, possibly infinite, so that the series converges L-adically. Then, this formula here says that for any value of k, we can get the value of the series at Pz plus k by applying this affine linear map to the F series at Z. The key thing to note here is that if this thing converges in QL, then it's in the domain of this affine linear map, which then automatically gives us this thing. And so the formal identity then gives us the equality of these two. In other words, and this is really the key thing that's going on, these maps right here, these affine linear maps of QL, they act as transitions that allow us to go from one side of the functional equation to the other. Then the fact that this works is because these maps aren't just affine linear, they're continuous, and in fact they're homeomorphisms. So they're going to map QL convergent series to QL convergent series, and their inverse is going to do the same. This aspect of the argument actually occurred at a key step in our proof of the correspondence principle in episode 3, where we used the fact that each of the branches of the shortened QX plus 1 map was not only was it continuous on the 2 adics, it was also continuous and invertible on the Q adics as well. Yeah. So in this viewpoint, we can regard F series as natural series representations for the formal solutions of systems of affine linear functional equations. In, is this my dissertation? Yeah. In my dissertation and in my papers, these functions arose by considering solutions of the functional equations and then extending them from N0 to Zp. In all these cases, the fact that the affine linear maps, like phi k, are homeomorphisms of QL play a pivotal role in our arguments. And so basically the reason this all works as follows, is that given a K-frame F, let alpha and beta be constants in the base field K. Then, and suppose further that this affine linear map is invertible on K. Then, for whatever topology we give K, this map will be a homeomorphism from K to itself. But moreover, whenever we take a completion of K, phi will extend to a homeomorphism of that completion. And that's exactly what happened here. Even though S is converging L-adically, the RKs are rational constants. So this is technically, the phi k is a rational affine linear map. And so it then extends to be an affine linear map on any completion of Q. And that's the power here of why everything works. So now what's really important, this is something that I did in my dissertation, is that we can conjugate these functional equations to get other solutions. So choose a frame F on Zp, a Q frame, such that our given F series is compatible. Then letting alpha, beta be in Q, or if F is a completion of K over which our F series condenses, we get a compatible function by the formula alpha times S of Z plus beta. Again, because alpha and beta are rational numbers, then this is going to be in whatever completion of Q this quantity happens to be in. Playing around with the just the functional equations, we then get f of pz plus j. It's alpha of times that. So we're using S's functional equation. Then we rearrange. Let's add and subtract beta rj so that we can factor out the rj, and then this is of course f of z, and so we get f of pz plus j is equal to rj f of z plus alpha plus beta times 1 minus rj. As such, for any alpha and beta in Q with alpha not equals 0, f satisfies a system of functional equations of this shape, where gamma j is here. So now where am I going to, where do I mention this? Let's see. Did I put it down here? Did I put it down here? I think I put it down here. What? Where did it go? Okay. This is weird. I thought I included it. Okay, sorry about that. blah, 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 blah. Oh, no, here it is. I skipped it because I'm stupid. Okay. So, sorry about that. So, we have a contraction. Everything is nice. Now, if you happen to be particularly clever, you'll notice that there's a linear algebra problem that occurs here. In this case, this constant really, the RJs are given. So, in terms of conjugating things, we only have two parameters here. But we have, since this since this function has J, so it has a P distinct functional equations, when we consider F's functional equations, here is a system of P functional equations, but the transformation factor only depends on two variables. What that in particular means is that the only way we'll get a non-degenerate solution is in the particular case when P is equal to 2, when we have a polygenic F-series of polygenicity degree 2. And we're going to need to modify that in a way to deal with F-series where P is greater than or equal to 3. But anyhow, so the reason why all of this stuff is really nice and what I've been heading to is that with frames at our disposal, we can now give a much more expansive treatment of the correspondence principle. And the reason why this all works is, again, it comes down to doing things pointwise. If you go back and look at the proof from episode 3 of the correspondence principle very carefully, you'll notice that whenever we considered this limit, it was always being studied pointwise with respect to z. That is, we fixed a z and then we did all of our arguments. Because of this, we can repeat those arguments verbatim for an arbitrary hydromap, even polygenic ones, provided that the Newman of the hydromap extends to be a rising continuous function with respect to some Q frame, F. And now here, notably, F doesn't need to be a frame on all of the P adics. So now let's go back to our dragon map. This is the map on the Gaussian integers, which divides z by 1 plus I if z is a multiple of 1 plus I, and otherwise will add I to z. This, as we saw, this admitted a Newman chi d defined on the set z2 take away s, and it was complex valued, and it was characterized by it satisfied these functional equations for all z in this set, and subject to this rising rising continuity condition. And here, S was defined as a set of all two-adic integers such that the lim sup of the number of ones in z mod 2 to the n over n is equal to 1. This is, in other words, the S here is the set of all two-adic integers for which the number for which the ones digits have density 1. In other words, S is the two-adic integers whose almost every digit is 1. Now, we're going to do a little bit more here. We're going to consider IN is going to be the average of the complex absolute value of chi d of n. We are now arguing recursively. IN is equal to this, and so now we're going to split this sum up into the evens and the odds. We then apply chi d's functional equation, and here we use the fact that 1 plus I has a complex absolute value of the square root of 2, and then here we just use the triangle inequality. This is chi d of n's complex absolute value plus 1, and so what do we get here? This is IN minus 1. It's everything we have here, but with big N replaced with big N minus 1. This is 1/2 because we're summing from 0 to 2 to the big N minus 1. We're summing 1, so that's half the number of half of 2 to the n. And then we have 1/2. We factor out a 1/2 to make this exponent decrease by 1. We'll then get a 1/2 of I n minus 1. So this IN is bounded from above by 1/2 plus 2 plus root 2 over 4 times IN minus 1. And so, doing things recursively, we end up with a geometric series, and then checking that I0 is 1 over 2 to the 0, 2 to the 0 minus 1. This is just n equals 0, which is 0. we then have that In is less than or equal to this geometric series. Since this quantity is about 8.53, this upper bound converges as n goes to infinity. And so by the m-test, we then have that our In here converges in the reals. This, of course, is precisely the two-adic Riemann sum of chi d of n. And so what we've just proven is that chi d is in L1. It's integrable with respect to the the real valued two-adic Haar probability measure. A near identical, and so in particular, what this says is that chi d. It also tells us that z has to have measure 0 because the integrability of this necessarily means that the set of discontinuities of not the discontinuities, the set of points where chi d is undefined or unbounded has to have a 0 measure. And so a near identical argument to our recursive one here, but with this sum, without the absolute value, can then be used to compute the integral of chi d without the absolute values. When we do up the recursive argument, we end up getting this. And so then after writing 1 plus I over 2 as e to the pi I over 4 over root 2, we end up getting this. And so this has absolute value, complex absolute value 1 over root 2. As n goes to infinity, this tends to 0. And so we're left with that the complex valued integral of chi d of z dz is equal to 1 minus I over 2. If we then divided this quantity by 1 minus I over 2, we would then have that this, we would then normalize this to make this a complex valued probability measure or something like that. Anyhow, so note that there's just something quite important here. So in this case, for this particular function, the set of the frame that we've picked assigns the complex topology to every point in Z2 except the points in S. And understand the behavior of the function at those points in S is actually quite telling. And also note that this is an example of a function which is rising continuous on a subset of the two-adic integers, which contains the non-negative integers. So where does that say? Yes. So here, where is it? Yes. So the string theoretic construction of chi d tells us that if we have a d with infinitely many ones, of a z with infinitely many ones in it, the one way to get an element of S is to consider a z which has infinitely many ones in it. Yeah. So in particular, if we have a z is in as a and also something to note is if you have a two-adic integer whose sequence of digits is eventually all ones, then that two-adic integer has to be a negative integer. And so if we evaluate chi d at a negative integer, let's remember the string theoretic construction. The digits of z correspond to the branches that we apply. So if our z has infinitely many ones, or even just a density 1 of ones, then we're going to keep applying the odd branch. The odd branch of our function is z plus I. So what this is telling us, and is the reason why this function is not defined when z is in S, is because z in S corresponds to those composition sequences where we apply so many plus i's that are the divisions by 1 plus I aren't enough to cancel it out, and what we end up with is that chi d of an element of S will be equal to positive imaginary infinity. So those are all singularities of our function, and that corresponds to the fact that those composition sequences are divergent. Moreover, and this is something cool, note that such a sequence cannot occur because, as we proved earlier, this map is contracting and eventually will map everything to a small handful of cycles. So in particular, what we can say here is that the z's at which our Newman is undefined then represent trajectories which can never happen, period, because the nature of the map or dynamical system forbids it. So the good news, though, is that none of this is that this trouble has nothing to do with the periodic points of our dragon map, and this is because our periodic points cannot have a density 1 sequence of 1s in the associated z's, because otherwise it would dash off to infinity. Now, again, as we said, part of the problem here is that we don't have enough constants. And so this identity with this F-series, it works fine as long as P is a 2-hydra map. However, when we consider P greater than or equal to 3, then problems emerge. In particular, when P is greater than or equal to 3, this F-series construction here, we cannot conjugate it to an arbitrary hydra map. Rather, we have a limited freedom. However, there's a way to modify the F-series construction even further to get an F-series that can be conjugated to pretty much any P-branched hydra map for any P. And I call these foliated F-series. These I covered in my dissertation. The trick here is that it's going to be sum from n equals 0 to infinity. Again, we have our product of RJs, but we modify this by the inclusion of this factor right here. Here, epsilon of z, takes values in roots of unity. For every p-adic integer z, it outputs e to the 2 pi I over pn plus 1 times z mod p to the n plus 1 minus z mod p to the n. So this actually was something quite interesting. When you go through the kind of computations that we did in episode 4 to find the Fourier transform of chi-q, when you go through that for a p-branched hydra map, the cardinality of the non-zero elements of the finite field of order p ends up playing a key role. You end up getting a projection. In particular, this is just a fun fact. If you take what is it? A projection ends up arising, and the projection it behaves from p equals 2. The projection always outputs 1/2. When p equals 3, it outputs either 1/3 or 2/3. When p equals 5, it outputs either 1/5, 2/5, 3/5, or 4/5. And more generally, for any given p, this projection factor, which results in this thing, involves a function that whose values depend entirely on the numerator of an element of zp hat. And the numerators of a non-zero element of zp hat is always going to be congruent mod p to one of the invertible elements of fp, the field of finite field with p elements. And so in this case, as I show in my dissertation, the foliated F-series, in addition to satisfying all the functional equations, they have more flexibility when you conjugate them. So that, unlike the ones that we considered before, where you really only have 2 parameters you can work in with your conjugation, these you have p parameters that you can work in. So to extend our arguments for the CP, the next thing we need is a way to compare different frames. And to that end, let K be a global field, and let F and G be K frames. I say G dominates F, denoted like this, whenever the support of F is in the support of G, and whenever for all x and x, the places that F specifies at x is a subset of the places that G specifies at x. Here, recall that support of F is the set of points in x that we're keeping track of, where we have semi-normals associated to them. So, and in here, what this is saying is that whatever places F spits out at x, G spits them out too. So then the proposition is, let F and G be frames with G dominating F. Then for any F that is compatible with G, the restriction of F to the support of big F is compatible with big F, and this is immediate from the definitions. So now, specifically, let chi be an F-series on ZP, like a foliated, but in general foliated. Then any Q frame big F, which is compatible with chi, is dominated by the Q frame G, defined by Vz of G equals the places of V of Q, so that chi Z converges in QV. This construction here is what I was talking about before when we were doing that big messy analysis with the system of equations. In general, this is going to be that you get what I call the maximal compatible frame for chi. It's where you throw in all of the places that it converges pointwise. And this is in general, it's going to be a thick frame. And so with this, we have the following. Let H be a p-hydramap with a Newman chi H, and suppose there is a unique suppose. Then there's a unique foliated F series and a maximally compatible Q frame F with whose support contains N0, so that our Newman extends to an F rising continuous function, which is precisely equal to the F series on the support of F, subject and no, there should be an there should be an HJ here. The jth branch of H. This is wrong. It should be S of PZ plus J is F equal to HJ of S of Z, where HJ is the jth branch of our hydramap. And though I do not state the result in this form, this is the bulk of what I showed in section 4 of my dissertation. And so now we have the big fun result. Let H be a p-hydramap with a Newman here, and let F be the maximal compatible frame for chi H. Then X is an integer X is a periodic point of H if and only if there is a rational p-adic integer Z and a possibly infinite prime in Vz of F, so that the chi H of Z mod p to the n converges L-adically to X. Moreover, the map which sends a given X associated to the associated Z is a bijection from the set of periodic points of H and Z to the set of rational p-adic integers at which chi H attains rational values. So what this is saying is the periodic points of H are precisely those integers which are the values attained by the F series in some topology at some rational p-adic integer. We also then have the divergent point, the halfway form. If X is a divergent point of X is a divergent point of H if there is an irrational p-adic integer Z and a possibly infinite prime in Vz of F, so that chi H of Z mod p to the n converges L-adically to X. And then the proof, just the sketch, everything proceeds almost identically to what was shown in episode 3. The idea goes back to what we talked about in the beginning of episode 3, where we considered arbitrary composition sequences of the branches of H. As we saw, the periodic points of H are going to be fixed points of composition sequences. The functional equation satisfied by the foliated F series from our lemma then shows that every such periodic point will occur in the image of the F series, and that if the F series takes a rational integer value at a rational x at a rational p-adic integer, then x must be a periodic point. Indeed, we actually have the more general statement that a rational number x is fixed by some composition sequence of H's branches if and only if the foliated F series outputs X at some rational p-adic integer Z. That is to say, the rational values that our F series attains are precisely those rational numbers which are the fixed points of some composition sequence of branches. The existence of the place prime, place/prime L for which the limit exists, guarantees that there's some topology for which the F series converges, and for which we can use its functional equations to prove that the values it takes are periodic points. Note also that we're using geometric series universality here, because when Z is rational, the F series will end up becoming a linear combination of finitely many geometric series, and as a result, the rational number to which they converge is independent of the choice of topology in which we sum the series, and that's why we can choose any L. Yeah. Finally, the divergent point criterion arises from the trichotomy of the dynamic of the orbit classes of a dynamical system on the integers. In particular, as we saw, every orbit class of a map on the integers is going to contain either a cycle or a divergent trajectory. Like we saw in episode 3 with chi-q, we observed that if the foliated f-series S takes a rational integer value, s of z0, at some irrational p-adic integer z, then if s of z0 was pre-periodic, we could then add or remove finitely many p-adic digits to z0's digit sequence, and then obtain a z1 from z0, so that s of z1 was a periodic point. But then z1 would be rational, and z0 differs from z0's digits differ from z1's digits by only finitely many terms, which then would force z0 to be rational, which is a contradiction because we were given that z0 was irrational. And then the use of the places here is simply required to sum this quantity. So once the sum exists and we know that it's an integer, the trichotomy of dynamical systems then forces S of z0 to be a divergent point. In particular, and actually this leads to the converse of the correspondence principle for divergent points, which is that every divergent point of H, every integer divergent point of H, is the value of the associated f-series in the Newman in some L-adic topology for some irrational p-adic integer. Now, here's a really interesting question that I honestly don't know. I'd say it's a coin toss either way. Suppose Z is a irrational p-adic integer so that the Newman converges to a rational integer in the L-adic topology. If we pick a different prime and guarantee that, so the L1 adic topology. If we pick a second prime, L2, and suppose that the Newman converges to an integer L2 adically at the given Z, is it guaranteed that those two integers are going to be the same? We know that if Z is a rational p-adic integer, they will be, because even though we're using two different topologies to sum the same series, geometric series universality comes home, and it brings us home to the same quantity. But what I'm asking is, what if Z is irrational and it converges in L1 adically and L2 adically to integers x1 and x2? Are x1 and x2 necessarily the same integer, or could they be different? In which case, what that would then mean is you could have a irrational p-adic integer z such that the value of the Newman at z varied depending on which topology you picked. Yeah. So anyhow, the moral here is that the correspondence principle seems to only care if there exists some topology in which the f-series of our Newman converges. As a result, if we only consider the behavior of a function like chi-h with regard to only a single topology of convergence, we're immediately closing ourselves off to information that could be obtained by considering a different metric completion. So now let's just finish up this part of the episode with some Fourier analysis. So from the perspective of classical analysis, the foliated f-series and all that stuff, then the polygenic things, they're horrible. They're impossibly nightmarish. And these functions seem pathological beyond belief because they are not only are they not necessarily converging in the reals, but they might be converging p-adically for multiple primes p, which is crazy. Yet, in fact, we can make for any finite number of different metric completions of the base field, we can make f-series that converge in all of them at different varying points. Yet, as awful as these functions might seem to be, when we consider them from a Fourier analytic point of view, a magnificent structure appears. So this is going to be like advanced rehash of what we did at the end of episode 4. So fix a prime p and let q0 through qp minus 1 be non-zero rational numbers, and set f of n to be this product, where recall the number of zeros in the p-adic digits of n, it's defined to be lambda p of n, the number of p-adic digits of n, minus the number of ones, the number of twos, etc., all the way to the number of p minus ones. This is important because then it guarantees that f of 0 is equal to 1. Now, letting qj denote, a big qj denote little qj over q0, we can rescale things. And we pull out the q0, and then we we divide this and bring it in and out, and we end up getting that this thing is equal to q0 of lambda p of n times this j equals 1 to p minus 1 qj times the number of j's in the p-adic digits of n. So now we're going to do our Fourier series analysis, our Fourier series analysis. So recall the idea of what we were doing in episode 4 is that chi-q's integral, in particular its Fourier integral, diverged. So what we instead did is we truncated it, considering chi of z mod 2 to the n. We integrated that, we rearranged it, and we extracted the part which diverged as n goes to infinity. That's what we're going to do here. So here let h of t be sum from k equals 0 to p minus 1 of qk e to the negative 2 pi I kt, and let gn of z be, we're going to take f and we're going to evaluate it at z mod p to the n. Then the Fourier transform of gn is this thing. And so for ease of reasoning, just note that these two, that's this here. And so then let's just work with the integral. The Fourier transform of gn is gn hat of t, that's this integral. Since gn is locally constant mod p to the n, this reduces to a Riemann sum. Here, since we're taking things mod p to the n, g big N of little n is going to be equal to fn for n in this range. And now we use our factorization of f. And here we're now going to apply the functional equations to get a recursive relation. We're going to split things up mod p, so we go from n to pn plus k everywhere. And now we apply our functional equation identities. This is going to end up, we get out a factor of q0, except when k is non-zero. This right here is the k equals 0 term. And then for all of the other ones, we get this. In particular, this is the k equals 0 term, and this is everything else. And so this is just something, each of these will give us a qj, and then we're going to sum over all of the k's, and so we get that right there. And this, we just recognize that this is gn hat of p, this should be an n minus 1. This is gn minus 1 hat of pt, and that's because the p and t are right there. And then we just play around with things here. The sum from n equals 1, this is just the same thing as if we take the n equals 0 term and subtract it. So this is gn minus 1 hat of pt minus 1 over p to the n minus 1. And so lots of details. We then just play around with things, rearrange, rearrange, rearrange. This is h of t, and we get our recursive relation, just like we got for chi-q. And now we just nest it. Nest, keep track of the pattern, and this is as follows. So all we need to do here is now compute g0 hat of p to the nt. Well, when we have n equals 0, this is always going to be 0. So this is f of 0 times this integral. And this integral, of course, is the indicator function of 0 times p to the nt. This is going to vanish if t has a p-adic absolute value less than p to the n. Is going to be equal to, greater than p to the n, and it's going to be 1 if it has the p-adic absolute value less than or equal to p to the n. And so plugging that in, we get this guy. And then to finish, we note that since gn is locally constant mod p to the n, its Fourier transform has to vanish for t bigger than p to the big N. And so we can stick in a free 1,0 of p to the n t, because this is the indicator function for every t which does not satisfy this property. And then that gives us what we want. And so for non-zero t, remember this term right here corresponds to our AQ hat that we attacked. And the way we attacked it in episode 4 was we observed how it behaved with respect to n when t was fixed. And so in this case, writing this product out, we get the following. And so we note that when t is fixed, this will be 1 for all k, provided that n is large enough so that p to the n cancels out the denominator of t. In particular, we have the following. And where did I set big R? Whoopsies. Yes. So here, I should say, yeah. I forgot to mention. Let h of 0 be equal to big R. Then for a non-zero p-adic t in zp hat, and for all n greater than or equal to 1, we have that this product is equal to r to the power of the maximum of n plus vp of t, comma 0, times this guy. And so the proof here is it's exactly like we did in episode 4. If big N is less than or equal to negative vp of t, then we just get this. But if big N is bigger than that quantity, we can move out the product here. The observation that's key is that p to the n t is going to be an integer whenever n is greater than or equal to negative vp of t. And so in other words, once n is sufficiently large, this is going to, since h is a periodic function, mod 1, this is going to be equal to h of 0 whenever p to the nt is an integer. So just like with AQ hat, for fixed t, as n gets bigger, this function is going, although there's going to be this finite part, it's going to then just grow geometrically in R, where R is h of 0. And in particular, looking at this is h of 0 right here, and we're multiplying it a total of n minus 1 minus negative vp of t plus 1, because we have to do that, and then this gets us r to the n plus vt. And the maximum and minimum here are used to make this work as a single formula. So applying this formula to g and hat of t and working through all the details, and so here note that t is going to be between 0 and p to the big N, which is the same thing as saying that n is greater than or equal to negative vp of t, and so we can get rid of the minima, and we work through everything here, and so look what happens. This is just plugging in for the h products. This is for both the big N1 and the little n1. When we work through it, we get this right here, and we've now gotten rid of all the maximum. And again, here what we're doing is we're splitting up the n sum. We're summing from n equals 0 to negative vp of t minus 1, and then summing from n equals negative vp of t to big N minus 1. And we're doing that to break up these exponents so that we can evaluate the minima and maxima respectively. Then we do a recursiveness. Here, this is big Qj, which we defined as little qj over little q0. And if we factor out the little q0, we get 1 over little q0 to the negative vp of t, because that's the number of times we multiply this. That's the number of terms in this product. So now here is going to be our analog of AQ hat. It's p hat of t is going to be 1 if t equals 0, and it's going to be n equals 0 to the negative vp of t minus 1 of this function right here, for non-zero t. And we're then going, just to make things a little bit easier to work with in general, this function here, it depends pointwise on t, but we're then going to define this version with an n here. So in this case, we've allowed this product to vary depending on n rather than on t. Again, note that just as for future stuff, this here, going back to the stuff we talked about in episode 6, this is a p-power root of unity, and the qj's are rational, which means that the p hat is taking values in a p-power cyclotomic field, and so in particular we can then embed that either into ql for some prime l or into some cyclotomic extension of ql, and this shouldn't be an l power, this should be a p power not L. And so in particular, we then have that if we require this should be modified. If we require the QJs to be integers, then we're going to then have that this function and this function will be take values in the algebraic closure of QL, which means they'll be integer valued for they'll be L-adic integers or L-adic complex integers. So anyhow, if we continue with our analysis, we have this and this, and so we put all of the things together and rearrange it. So here what I'm doing is I'm just taking this horribly messy formula and I'm replacing it with this slightly less messy formula by using these identities to replace stuff. As such, then to finish this, we need to stick in this term to take care of the fact that this, this should be a big N. This should be a, this should be a big N here. But then, anyhow, what we proved is as follows: that the integral of f of z mod p to the n times the Fourier character, it's this messy part. So now what we're going to use is we're going to take this to figure out how to sum our polygenic F series. In this case, I'm going to simplify it a little more than the RJ version that I created, and I'm going to be considering one of the form, the product j equals 0 to p minus 1. Here the QJs are going to be integers, and d is going to be an integer. So this generalizes the form that we saw in last episode, the one with the 3 and the 5. And so all we need to do here is, now that we know what the Fourier transform of this guy is for any given n, we just proceed by linearity. So we're gonna multiply this quantity by 1 over d to the n, and then we're gonna sum from n equals 0 to big N minus 1. And do everything, and then note that this key factor appears. We have r over dp to the power of n and dp to the power of n. Play around with things, we get this. So what we need to do here is just to summarize, this we can just in examining this part, this gives a very nice breakdown of how this Fourier transform depends on n and t. And now that we've summed things up, we're going to need to massage it to pull out the parts that depend on big N. And so just writing all of these sums out, we get 3 terms. R to the VP of t, where little r is, I think I defined that as the sum of, I forget what I defined little. Oh, no, I changed it. I went from, no, it was, okay, I remember now. I must have deleted this. Little r is Q0 times big R. So that's going to be little r. Q0 times big R is little r. And yes, because that's right here. This is, yes. Yes. Q0 times R times big R is little r. And so, anyhow, doing this, when we multiply everything out, we get these 3 terms. And so, in particular, to deal with these things, we observe that as stuff varies, we really have 2 kinds of sums to deal with. Which is going to be either this or this, and then there's this sum here, but that's going to be a geometric series. These end up being sums of the form little n equals 0 to big N minus 1 of the indicator function times x to the n for some non-zero rational number x. And we can deal with these in a single computation. So this is going to be n plus vp of t if x is 1, and it's going to be this thing if otherwise. And so this is just showing the 2 possibilities for geometric series. You can either have it's degenerate and you get linear growth, or it's non-degenerate and you get a geometric growth. And in particular, when t equals 0, we get that this is going to be n and x to the n minus 1 over x minus 1, respectively. And the proof is very straightforward. And it just, again, it's about keeping track of the values of n for which p to the nt is a non-integer. And so the only other sum we need to deal with here is this thing. And so we get This computation gets messy, but there's an easy way to deal with it for all the different cases. This is the most general this is the nicest, I should say, it's the nicest case because it's r is not equal to 1, dp is not equal to 1, and r is not equal to dp. That's so that we can guarantee that this thing won't be degenerate and this thing won't be degenerate as well. And so the way we can do to make sense of this is if r equals 1 or dp equals 1 or r equals dp, just take the formal limit, like just pretend it's real numbers and everything, and just do the limit as you would in a calculus 1 class, use L'Hopital's rule, and you will end up getting the correct value. And so this is just, and if t equals 0, we end up getting this thing, and sorry, t is non-zero. And here t has to be non-zero so that this doesn't blow up. And this is, we end up getting this stuff, and the rest, this is what happens here, and the rest follows from using our identity. So now we just put everything together. Sn hat, this is the nth partial sum, the Fourier transform of the nth partial sum of our F series. If r is not equal to dp, and r and dp are not equal to 1, our analysis tells us that the Sn hat of t is going to be equal to this stuff plus divergent terms depending on n. If r equals dp and r and dp are not equal to 1, we get this stuff plus divergent terms depending on n. If dp equals 1 and r is not equal to 1, we get this stuff plus divergent terms depending on n. And if r is equal to dp is equal to 1, we get this stuff plus divergent terms depending on n. And this is just a matter of evaluating the messy limits. I'll let you guys, you can pause to look through it. So there's that. And so this is just what Sn hat of t looks like in the general case. And then we just will then formally differentiate these things based on, we'll formally take limits based on whether or not r or dp are equal to one another or equal to 1. And then doing all the sums and canceling out, we get everything we want. So there's that here. And then we have this here. And this here. And this here. So then in this case, the case notices that when r equals dp equals 1, these difference quotients is the limits, they both leave us with n plus vp of t, and so we're left with this. And since r equals 1, we take the formal limit of this, and we get that it's vp of t, and we get this, which is the plus the divergent terms. Now, just like with chi-q, what we're going to do is we're going to show that in all cases, when we sum the non-divergent part, when we sum this thing, we're going to end up recovering, and then take the limit as n goes to infinity, we're going to end up recovering all of S, our original F series. And blah, blah, blah. So in this case, note that what we've done is so far we're working with t not equal to 0. So we're going to be summing every term of the Fourier series but the 0th term. And then to figure out, and then we'll just define the 0th term for what we need to be in order to make everything work. An examination of these messy formulas shows that what we're going to need to do is consider terms of this form and this form, where c is a non-negative integer and x is a non-zero rational number. Now, the PM hat case is doable, but it's very, 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 very unpleasant. As such, we're going to ignore it. And the reason why we're going, and not the reason why, but actually yes, the reason why we can ignore it is if we look back at all of these formulas, I just want you to notice something. Here, when q0 is equal to 1, this goes away, and we lose the PM hats. Here, when q0 is equal to 1, this goes away, because it's 0, and we lose the PM hats. Here, when q0 equals 1, this goes away, and we lose the PM hats. And likewise, here, when q0 equals 1, we lose the PM hats. So this thing, the PM hats are error terms that are there to are correction terms that are there to deal with the case where q0 is not equal to 1. In particular, q0 not equal to 1, that corresponds to the case where the zeros digits of our p-adic integers are going to contribute to the value of the F series. When Q0 is equal to 1, the zeros digits will not contribute. And so things simplify much more when Q0 is equal to 1. And in particular, when we do this, we end up with the following, depending on the values of... so it's if R is not equal to dP and R and dP are not equal to 1, we get this, that, we get that, blah, 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 blah. And in here, a bit of thought shows that we can actually reduce this to just two cases. R is not equal to dP, and then Sn hat of t is this thing, and R is equal to dP, and then Sn hat is this thing. And once again, our key argument is going to be a combinatorial generating function identity involving f of k. And so this is done by using base p representations. And what it is saying is that the product from k equals 0 to n minus 1 of the sum from j equals 0 to p minus 1 of qj times z to the p to the k is equal to k equals 0 to p to the n minus 1 of f of k zk. And so this is just basic combinatorics. And then here we have this is going to be our main lemma, which we will use to sum our things. And here f of is this thing. And so this is this thing with z mod p to the n plugged in for k. And so the method for you proving this is our routine. It's our sum along level sets, and then use Ramanujan sum identities, and then re-index and cancel. And so in particular here we sum along for n equals 1, little n equals 1 to big N. And here it's the level set is we're summing along t with p adic absolute value equal to p to the n. And here we now use our generating function identity. This is what p hat of t is in general. Here's we now evaluate it using the fact that t's p adic absolute value is p to the n. And then this is the generating function identity. It turns this product into a sum. And the e to the negative k, this should be a 2, not a k, it should be a 2. Negative 2 pi I kt, and then we pull this into the p-adic fractional part, and we get the following. And so here, once again, we're going to use our Ramanujan sum, and here is little r. And so we're going to use this here. We're now going to manipulate things. So this is the Iverson bracket manipulation. This, recall, is going to equal p to the n times z congruent to k mod p to the n minus p to the n minus 1 times z congruent to k mod p to the n minus 1. And to bring everything together in order to prepare for the telescoping series term cancellation, we need to massage this a little bit. And so here we're going to break it up by summing from like this. So in other words, what we're doing here is instead of just considering k, we're going to we're replacing this with k, and then we're allowing the rightmost p-adic digit of k to be determined by j. Since this kills the Iverson bracket here, will kill things that are congruent to 0 mod p to the n minus 1. This goes away, and then we use the fact that f of k plus p to the n minus 1 j, the functional equation for f, then tells us that this is just the same thing as multiplying by qj, and then we use the fact that the sum of all of the qj's is r. And so we then get this is that. We plug this guy in, and now this is both an n minus 1 and an n minus 1, and so we have this. And so this right here, if you look, this is our sum. We're about to apply our reduction, and this is what we got after doing the Ramanujan sum. So now we're just going to break things up and re-index. And so the re-indexing here, this is going to become an n plus 1, and then we cancel. And it works out. And this part is very horrible. Just very horrible. Lots of details, because you have to deal with the zeros and the fact, the non-uniqueness of representations. And as you can see, it becomes quite awful. So anyhow, this at the end of this, we have the following. Let S of z be this F series, where f of an integer is there. And here, so again, Q0 is equal to 1. Let little r be that. And finally, let p hat of t be equal to this, where the product is defined to be 1 when t is equal to 0. If r is not equal to dp, let x be any set in zp containing n 0, and let f be any q frame on x which is compatible with s. Then the function s hat from zp hat to q bar, defined by s hat of t equals this guy, is a Fourier transform of s, and the limit is going to be equal to the sum. And suppose r equals dp, blah, 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 blah. And then for our frame, we just need that this condition occurs. Then the function s hat from zp hat to q bar, defined by this guy, is going to be our Fourier transform. So we are going to use our proposition with x equals dp and c equals 0. We get this. So now look what happens as n goes to infinity. If we pick a compatible frame, then that being compatible with s means that this converges. And so the convergence of this for all z with respect to f for all z and x then forces this term to go to 0 with respect to f for all z and x. So as n goes to infinity, this decays to 0 with respect to our frame, and then this, of course, is just going to converge to s with respect to the frame. So we get that. And so now all we need to do is just multiply through by dp over dp minus r. And here we use this fact. So then what we again, remember, this is summing over all non-zero terms. So we know that we sum all this. This right here is going to be equal to s of z minus 1. And so we get this, and so we then get the full Fourier series by just adding the constant term. So then this tells us that the Fourier transform of s of z is going to be this at t equals 0, and that for non-zero t. And we can write this as a single formula by noting that p hat of 0 equals 1, and that when t is equal to 0, this expression is equal to 1, and this expression is equal to vp of t for all t in zp hat. In other words, this expression with the minimum here, it covers both cases, because when t equals 0, this reduces to just dp over dp minus r. For r equals dp, again, we use our proposition. And then here we have to have this internal cancellation, but this is going to be equal to just negative 1, because this is, we assume r equals dp, so this is 1. So it's n minus n plus 1, which is just negative 1. And then we are left over with this. And then once again, it's just like before, since we assumed we are working with a frame f for which this goes to 0, this converges to 0 with respect to f. And since f is chosen so that s is compatible with respect to f, this partial sum will converge to s with respect to f. And then we're done. And then again, we can use this too. And so this then tells us that this function is a Fourier transform of s, and this function is 0 when t equals 0, so that we take care of that, and we're done with this part. So what this analysis reveals a very interesting way in which we can think of certain subrings of C rise of f. When r is not equal to dp, we have that for any prime number L, the L adic absolute value of s hat of t, just go through the motions, blah, 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 is this thing. So this right here will be finite if and only if L is coprime to dp, in which case s hat will be L adically bounded. Thus, our standard Parseval-Plancherel construction will then realize S as a PL adic measure, and then S hat is the Fourier-Stieltjes transform of that measure. A similar argument applies when R is equal to dp, and we end up with the following. Let L be a prime number, then our Parseval-Plancherel formula defines a PL adic measure if and only if L is coprime to dp. And so I'll talk about quasi-integrability in a bit. And so then this gives us a way of integrating S of z. We treat it as a measure, and we get this formula. And in particular, we then have the formal inclusion that S itself, if we identify S, the F series, with the measure it induces, we have that S is contained in the intersection of the dual of the continuous PL basically this is contained, it's the space of P of PL adic measures for all primes L which are co-prime to dp. So what this shows is that there are elements of our that can be utilized as and so we can think of that, or at least an appropriately chosen subspace of it, as being contained in the dual of this thing. So this would suggest that it would be of interest to study spaces which are given by intersections of PL adic measures over various collections, either finite or infinite, of primes, including of prime numbers. Indeed, it seems reasonable that the F-norm constructions used in the previous subsection might be helpful in giving this Banach space a metrizable, or at least actually I'm not actually this is weird. This is the space of measures, although it's a Banach space, it is also a vector space, and so what although we know the intersection of two Banach spaces is a Banach space, that's only if they're Banach spaces over the same field. When for two different primes L, these will be Banach spaces over two different fields. So, yeah, this is going to be a vector space, definitely over Q bar, the algebraic numbers, because the algebraic numbers are contained in CL for all prime numbers L, but of course we have to pick an embedding first. But so then this, very least, this is going to be a vector space over Q bar, and then again, if we can use our semi-norm constructions or F-norm constructions to potentially make this into a locally convex or possibly even metrizable. Would it be a ring with respect to convolution? But again, there's lots of open questions here. And so next time for the last part, we're going to study something really cool, which is quasi-integrability.